Hi everyone, I'm Mikhail. Welcome to the Dark Wire Labs YouTube channel, where we break down network technologies and bring them to life with real code. In today's video, we are leveling up the custom VPN protocol we built in an earlier lesson. We are moving beyond simple connectivity to add the two pillars of secure networking, peer authentication and data encryption. If you missed part 1, where we built the core architecture from scratch, definitely check that out first. To catch you up, we developed a C-based protocol that encapsulates IP packets into UDP datagrams. It's lightweight, handles net traversal, and we've already successfully deployed it across Docker containers, AWS, Cloud VM, and even cross-compiled it for an OpenWRT home router. It works, but right now it's completely insecure. Today we fix that. To design the new security layer, I teamed up with ChatGPT to brainstorm the architecture and refine the code. We decided to stick with a modern, high-performance approach by using Charger-20 stream cipher. Unlike AES, which processes data in fixed blocks, Charger-20 generates a continuous stream of pseudo-random bits to mix with your data. It offers constant time encryption and decryption, making it incredibly fast in pure C without needing specialized hardware instructions. Charger-20 is already baked into modern OS kernels and is the same primitive used by the industry leaders like WireGuard and Quick. To implement this, we are using Lipsodium crypto library that's already available in OpenWRT. Before any data can be encrypted, our client and server need to prove who they are and agree on a secret session key. We designed a three-way handshake to handle this. First, the client sends 32 random bytes to the server. Then, the server responds with its own 32 random bytes. Then, the client sends a hash-based message authentication code. This uses a pre-shared secret key and cryptographic hash to verify the integrity and identity of the peer. Once the server verifies this HMAC, both sides derive a symmetric session key. From that point on, every packet moving through our UDP tunnel is fully encrypted and authenticated. Let's dive into the C code and see how we integrate Lipsodium to make this handshake a reality. I'm using the same project folder, but here are our updated C programs for the client and the server, now with encryption support. The file, the Docker file, and the shell script to deploy this, they remain the same, just with small differences. For the shell script, I had to define the pre-shared key, which we need to use as additional argument when running the client or the server. So when running it, we need to supply this argument here inside the container. And both client and server will use this pre-shared key for our demonstration. I also added a command to run TCP dump on the physical interface of the container. It's only for the server, because it's inside this condition, the server only, and to save the packet capture in this file. And it will also run in the background and display the process ID, so we can kill this program later. Why I want this? Because I want to capture packets for the initial handshake, and also to show you the captured encrypted payload. Go into Docker file, and I remind you that we are using a single container, but we will run 2 instances of this container, and we only mention in the arguments whether it should run as the server or as the client. So the Docker file is just one file. Here in the dependencies, I added libsodium dev package. And yeah, we also need to add it in the compiler, so the compiler imports this. And these are modified programs for the client and for the server. So yeah, as you can see, the client now is also expecting to receive pre-shared key, same as the server from the arguments. Okay, now let's build this container. I keep the same container name like in our previous video. Okay, successful. Let's run the server. So we run the server, we use existing container network to net. Yeah, that's our tunnel IP address, and that's the port to listen on. So as you see, TCP dump started, the process ID is 10, and the server is waiting for a client to connect and initiate the handshake. Let's run the client. Another instance of the container. That's the interesting part. So you see that the server received connection from the client. The client sent RC value, what is 32 random bytes of data. Server received it, and then server sent RS value, also 32 random bytes. Client received it. Then client sent HMAC to the server. Server received it and confirmed that it's matching, so authentication is successful, and both client and server derived session key. Obviously it's the same. It will be used for data encryption and decryption because this is symmetric protocol, CHA-20. Okay, now I will open Docker desktop. Because I want another connection to the server container. Okay, looks like it's hanging. That happens sometimes. I'll stop the task. All right. Here we go. Okay, good. Container is still running. I'm going to the server. I'm validating this is the server. And I'm initiating a ping to the client. The client is responding, and this traffic is sent through encrypted tunnel. Good. Now to compare, let me ping the physical network adapter. I call it physical, of course it's not physical, but the real network adapter of the client, because I also want this traffic to be captured. Good. So it's working. Now I'm going to kill my TCP dump process. Killed. And in the server log I see that it exited and 65 packets captured. Going to files, server pcap, saving it locally, and let's take a look. Okay, this is initial handshake between client and server. This was client, we can call it client hello, server hello, and that's the third message where client sends HMAC, the hash, to the server. So handshake was successful, and then we see encrypted data. Actually, this is when I was running the ping. This was something else. If you take a look, we will not see anything. I mean, just data. Of course, Wireshark will not decode it. But what we can do, first we can just to confirm that this is UDP, it's encapsulated in IP. Okay, good. And we can also compare the size of the packet. So we see the difference is like 56 bytes. It means that the overhead of our VPN protocol is 56 bytes. So if we use it, we will need to consider to use smaller MTU for packets going through this tunnel. And also if we say if I have a client and the server somewhere in the cloud and I want to access some resources through this VPN tunnel, I may need to adjust, if this is TCP traffic, I may need to adjust TCP MSS value so that my application will understand that the MTU for this tunnel is lower, and because of that also the size of the TCP segments that are encapsulated in packets, they should be fit accordingly. Let me know in your interest if you are interested in this topic, and I can record another video about packet fragmentation, MTU, TCP MSS, and all this stuff. All right. Just to summarize what we did today. So we enhanced our VPN protocol by adding handshake for authentication and also data encryption. Now it's more secure and we can use in public environments. Of course, our protocol, it still lacks replay protection, it still lacks data integrity checks. And if you are interested, let me know in comments and I can show it in the next videos. I hope you enjoyed this lesson. See you next time. Bye bye.